Welcome all at the TCS seminar at Jagiellonian University. Today our speaker is Michał Pilipczuk from the University of Warsaw. Michał is a frequent visitor and colleague, but this time the reason is special. There is a breakthrough result in graph structure, graph minor theory, and we are all here to listen, Michał. Thank you for coming.
Thanks a lot for the introduction to the invitation. So first of all, I would like to just say probably I will disappoint you. It is not really a breakthrough in graph structure theory, because most of the stuff that I will be speaking about will be mostly on the algorithmic side rather than the graph structure side. But still, the result is that we can do minor testing and disjoint paths problem in almost linear time in general graphs. And this is a joint work with Tuukka Korhonen, who is now finishing his PhD studies at the University of Bergen in Norway, and Janos Stamulis, who is now a postdoc in Warsaw in our group. Good, so let's start. And first of all, let's define the problems that we will be speaking about. So minor testing and disjoint paths, and these are two most basic topological problems that one can consider in algorithmic graph structures. So probably, I hope all of you are familiar with the notion of minors in graphs, but let me just recall the definition. So this is the basic definition of what does it mean to embed one graph in another graph topology. So I will say that a graph H is a minor of a graph G if there is a minor model of H in G. So what is a minor model? Maybe instead of giving a formal definition, I will draw a picture first. So here is our favorite graph H that we would like to embed in some larger graph G as a minor. And the idea is that every vertex of H should be modeled by a connected subgraph of the graph G. Yeah. So I take every vertex of H and I sort of smear it into a connected stain in the graph G. Yeah. And the rule is that whenever two vertices are adjacent here, the corresponding stains that are in graph G should be also adjacent. Yeah. So these stains are often called branch sets of different vertices of H. So formally speaking, a minor model is a mapping eta that maps vertices of H to connected subgraphs of G, such that those guys are disjoint, and whenever two vertices are adjacent in H, then the corresponding branch set should be adjacent. Yeah. So, for example, one important usage of this notion is the Kuratowski theorem, which characterizes planar graphs as exactly those that do not contain K5 or K3. Yeah. So, given this definition and the importance of the minor order in the whole graph structure theory, there's a natural algorithmic question, namely testing whether a given graph G contains some small graph H as a minor. Yeah, so let's call this problem H minor testing. Yeah, where in the definition of the problem I have this graph H fixed. So the problem is given a graph G. The question is, does G contain H as a minor? Yeah. So, for example, you can reduce planarity testing to this kind of a problem, because in order to test planarity, it's just requires to test whether there is a K5 or K3 minor in the. But more generally, whenever C is a minor closed class, then by the theorem of Robertson and Seymour, the graph minors theorem, C is characterized by a finite number of forbidden minors. Yes, so this Kuratowski theorem is not a coincidence. So planar graphs are closed undertaking minors, so they form a minor closed class, and they are characterized by forbidding two forbidden minors, K5 and K3. And in general, it is the case that whenever you have a class that is closed undertaking minors, there's also a finite list of minors that characterizes this. For instance, if you think about graphs that can be drawn on a torus, they also form a minor closed class, and there's a finite number of those minors, actually a pretty long list, such that a graph can be embedded on a torus if and only if it doesn't contain any of those finite numbers. Yep. So then testing whether a graph can be embedded on a torus reduces to asking this question for each and every of those from this finite list. Yeah. And this happens for example for every surface, but also for many other topologically motivated classes of graphs. Yeah. So getting an efficient algorithm for minor testing immediately implies getting an efficient algorithm for testing membership in minor testing. Good. So this is problem number one that we will be speaking about, and problem number two is disjoint paths.
Sometimes it looks like no.
Yes. Actually, there is only a handful of classes where we know the complete list. Even for toroidal graph, I think the list is not really known. It is known to be at least of length 15,000, as far as I remember. It is known for projective plane. There are, I think, 95, something like that, graphs that characterize graphs embeddable in the projective plane. Good. So the second problem is disjoint paths. Yeah, and the input to this problem, I get a graph G and a bunch of pairs of terms, which are vertices in my graph, S1, T1, S2, T2, and so on up to Sk. Maybe I will draw here an example. Here is my graph G, and maybe I have here first terminal pair, S1, T1, maybe here a second terminal pair, S2, T2, and maybe a third terminal pair, S3, T3. And the task is to connect those terminal pairs by paths that do not cross, that do not intersect. Yeah, so the question, are there paths P1 up to Pk such that Pi connects at I with T1? Yeah, so the solution here could be, I don't know, a path. Maybe I will connect S2 with T2 using a path like that. Now I need to avoid this path, so maybe I will squeeze my path here, the orange path, and maybe the red path will look like. This is how a solution could look. Yeah, and as you see, it was pretty non-trivial to get those paths non-crossing, and indeed this problem is NP-hard in general. But the thing is that it can be solved efficiently, and we will see in a moment in what running time for every fixed k. So maybe I will even state the result here. There is a theorem of Robertson and Seymour that was proved in the graph minor series that this problem can be solved in time OK and Q. Yeah, so this notation, there's n cubed, this is n the number of vertices of the graph G. Yeah, and this notation OK means that there is a factor depending on k standing in front. Yeah. And similarly here, this is a very good question. From the currently put on archive work, it follows that it is computable. Yeah. At least this is what I believe. I don't think that it is known to be elementary. But I think it's safe to say that we already know that this is true and is computable. What Robertson and Seymour wrote in the graph minor series is more in the vein of, for every fixed k, there is a cubic time algorithm. So this is the statement that are there in the graph minor series, but then there was a subsequent work. I will comment on this later. And similarly here from the graph minor series, what Robertson and Seymour proved is that H minor testing can be done in time OH of MQ. Yeah, here again, this factor depending on H is horrible, but hopefully computable once everything gets published. Good. So you see here two problems. They're kind of similar. It's about putting some connected subgraphs in a given graph that have a certain pattern of adjacency. So it would be pretty nice to actually have some kind of a common umbrella problem that encompasses both of them. Yeah, and this is actually the problem that we will be working with most of the time today. So this is the so-called folio problem. Yeah. But before I introduce the folio problem, let me say what are rooted minors. So imagine I've got a graph G, and I've got a subset of vertices X. Yeah, so maybe in my graph I have a few vertices that I care about, like for instance, terminals. And now I get a graph H. Yeah, but together with a graph H, I've got some mapping pi. That pi maps vertices of H to subsets of X. Yeah, so in other words, if I have here my graph H, then for every vertex of H, I have a specified subset of terminals that should be inside the branches of this guy. Yeah, so then I will say that H pi is an X-rooted minor of G if there is a model with, well, exactly those rules that are prescribed being contained in the respective branches. So more precisely, for every vertex U of H, the roots that are in the branches of U is precisely what is prescribed by. Does it make sense? Yeah, the definition. So now, what is the folio problem? We are given a graph G, we are given a subset of vertices X, and we are given some number delta, and the question is to compute all X-rooted minors of so-called detail delta. And the detail is just the number of vertices of H that are unrooted, so which are not prescribed any root. Yeah, so somehow maybe here there was another vertex yeah, that is not prescribed any root, so it is somehow floating around. Yeah. So observe that the number of different x-rooted graphs of certain detail is bounded by a function of delta and the size of x. Yeah, because they have at most like x plus delta vertices, and there's only so many different graphs on that many vertices. Yeah, so an answer to this folio problem is just a bounded size table saying yes or no. Yeah. The detail is the number of vertices of H. Yeah, so a x-rooted minor is H and a mapping pi, which says which roots should be in which branch set. Yeah, and the detail of this is the number of vertices of H that are not prescribed any roots. This is just one definition of those things. This is the definition that is actually used by Robertson and Seymour in their paper. You can define those rooted minors in 1,000 different ways, and which would be essentially.
This is H is not fixed.
Yeah.
Fixes delta.
Yes, I fixed the number of floating vertices and well the number of roots because I fixed the roots. Yeah, and now I would like to compute all possible minors, rooted minors.
So the possibility is like the number of vertices, which is at most x plus delta, and then you have some edges you can describe. You want this edge and that edge, and eventually you have this pi function.
Yeah.
And then the question is, can you do it or not? So
yes.
Yes or no question.
So the number of different x-rooted graphs is at most something like this square, yes, times the number of different pi's, and the number of different pi's is probably something like the size of x. That's a partition number. Okay, so a rooted minor. I will say that a pair H and pi is a rooted minor, where H is a graph, and P is a prescription where it's a mapping where for every vertex of H I tell which roots should be in the branches of this vertex. Yeah, so a subset of the roots. Yeah.
So roots are just elements of X?
Yes, roots are just elements of X. Yeah. So a rooted minor would look like that.
It's only element of X.
No, the branches is larger, but the intersection of
yes, the intersection of the branches with X must be exactly as prescribed. Yeah, I'm just saying, asking for existence of a minor model that has exactly those roots inside. Among all the roots, number 1 and number 2 should be in these branches, and no other root should be in these branches.
So going back to your picture that you drew over there with the regions, now for each region you prescribe which elements of X should be in it?
Yes, exactly. That's the whole thing. Yeah. So a normal minor would be a rooted minor for X being an empty set and pi being just saying empty set for everybody. So none of the branches is prescribed any roots. But for instance, I could model that disjoint paths problem and as asking for a rooted minor by saying that my H will be just an independent set of size k, and my pi will assign to each of them Si and Ti. A pair of roots. Yeah.
I think what was misleading is that actually the minor is not just H and pi, but it's a triple H, pi, and eta. Right?
Yes, in like eta is the minor model, witnessing that H pi is a rooted minor. Yeah, in the same sense as, I know, K5 can be a minor of G, which is witnessed by a minor model. Yeah. Right, but we will be working with this a little bit more technical notion of the folio problem because it encompasses both of those problems. It's also a good abstraction for various recursion steps that be done in that are done by the. Yeah. So what Robertson and Seymour actually proved is that folio problem can be solved in time order of the size, the number of roots and delta times NQ. So that's a major algorithmic corollary of the graph minor series, and this theorem actually immediately implies both that and that, because once I compute the folio for a large enough delta, then I can read simply from this folio whether H is a minor, and I can read from this folio whether the disjoint path problem has a positive solution. Yeah. So what is the history of this problem? So this is a result from the graph minor series. So it's unclear what year it was actually proved, but it uses most of the machinery from the graph minor series. The largest part is done in graph minors 13, as far as the proof of the statement is concerned, but there is a so-called irrelevant vertex technique that we will be talking about later in more detail, which is actually postponed, I think, to graph minus 22, I think. So actually, you need the almost last paper from the whole series in order to prove this result. So then people were asking whether this n cube can be improved. Yeah. So there's a paper. There's a result proved by Kobayashi and Reed, I think 2012, I'm not entirely sure, but they improved this to quadratic. Actually, in their paper, they only talk about the disjoint path problem, and they give such an algorithm for the disjoint path. But then at the end, there is a short section that is more or less arguing that all the techniques actually work for them. Also, what is in the paper actually gives you n square, I think, inverse Ackermann n, something like that. And they claim that they can shave off this inverse Ackermann using some unpublished manuscript that did not appear during the last 12 years. So just to say that, yeah, the literature can be confusing. So what we prove is that this we can do in almost linear. Now note that I wrote here m instead of n. So this is the number of vertices, this is the number of edges. So we are almost linear in the number of edges. Yeah. So the first note about this is that if we have for minor testing, or just minor testing, not rooted testing, we may assume that the number of edges is linear in the number of vertices. Why? Because if I have a superlinear number of edges in a graph, then by a result of Thomas and Kostoczka and essentially basic results in graph structure theory, if a graph has a superlinear number of edges, then it contains a large clique as a minor. Yeah, and if it contains a large clique as a minor, it contains a large any large enough graph as a minor. Yeah, so I can immediately say yes in this case. Yeah, so for just minor testing, this M can be replaced by M, but we are not aware of any sparsification method that for the rooted minor testing or even disjoint paths is able to reduce the number of edges to linear in the number.
So they log n, right?
No. So Kostoczka says that if I am KT minor 3, then the number of edges is bounded by the number of vertices times order of square root of t.
Oh, yes.
Yeah, so this is log, but of the excluded minor. Yeah, so this is a linear bound. So then if my E is larger, if my number of edges is larger than that, yeah, then I can immediately say yes. If T is the number of vertices of a graph H that I test. So maybe I'll write here in yellow, open get M equal to order of n in the rooted case. Yes. Okay, so this was note number 1 about the result, disclaimer number 1. Disclaimer number 2. Maybe I'll squeeze it still here. Note 2. So I wrote here this O notation with the constants here. Yeah. So now the question is, how does this constant hidden in this O notation actually depend on those parameters? So what we can again claim is that this constant in this is computable from the parameters, yeah, but subject to not peer-reviewed work. Yeah. So there is a paper, there's an article preprint of Paul Wallen, Robin Thomas, and Bruce Reed. Bruce Reed? No, sorry, Kenichi Kawabayashi. That does a lot of work in groundwork in the graph minors theory with explicit bounds, and in particular those bounds are computable. And subject to those bounds being correct, all of the stuff that we are now that we have here is also similarly computable. This is a manuscript that is on Archive, and as far as I understand, it is now being reviewed in a journal. So this is just a disclaimer that this is subject to this being holding. If you do not believe that, then we can still rely on just all the standard statements from the graph minor series, and then what we could claim instead is a non-uniform algorithm. So for every fixed size of x and every fixed delta, we can claim a almost linear. So this is disclaimer number 2. And disclaimer number 3.
How is this program?
Well, it doesn't.
That's not.
Yeah, this is like m to 1 plus small O of 1. You mean, yes? Yeah, this small O of 1 doesn't depend. Yeah, the disclaimer number 3 is about the small O of 1. So maybe this will be more enlightening to do it explicit. So this m to small O of 1, this is actually something like roughly 2 to the order of, I think, log to power 0.99 m. So it is a function that is, well, independent of x and delta. Yeah. It is sub-polynomial, but it is larger in polylogers than any polynomial. So this comes from the usage in this result of 3 black boxes. The first black box is so-called dynamic tree width. And this black box, I hope that we will see in more details in a minute. Then another black box is almost linear max flow. Yeah, so this is this large breakthrough that happened, I think, a year or 2 years ago of Van den Beant and others, that maximum flow in graphs can be computed in almost linear time. Yeah, and there is a third black box called mimicking networks, which is also another result within the cut community that incurs this kind of a block. And each of those 3 black boxes independently has this kind of a dependence on n. So in order to get a polylogarithmic dependence on m, here you would need to improve all 3 of them. Yeah, so, but hopefully in a subsequent work, at least for the non-rooted case, we can rely only on this black box, I hope. And this black box actually looks the most promising to get polylogarithmic. So this is just, I will comment about this later. Good. So this is about m, and these are, yeah, these were my disclaimers. So this is the statement of the result. Any questions at this point? Okay, if not, then let me try to start sketching. First of all, what is the standard approach to the folio problem, or the disjoint path problem, or the minor testing problem? And then we will see the sort of an outline of what we are doing. We will definitely not go into the details in any reasonable sense. The paper is, I think, 85 pages long, and it's like 85 pages of tricks all over the place. There are 4 steps that we are doing. I hope to be able to show you step number 1 in reasonable details, step number 2 in maybe a little bit less details, and then it will become more and more blurry along the way, once we will be going to more and more general classes. But I hope that maybe the overall picture, I hope that should be clear. And I particularly want to show you step number 1, which is the step where we use dynamic tree width, because this is the step where actually conceptually the most new part happens. But generally, what is the classic approach to the folio problem, and what is our approach to the folio problem? So the classic approach to the folio problem is irrelevant vertices. And this is the basic approach that was devised already, proposed already by Robertson and Seymour. And so far, essentially every algorithm for disjoint paths or this kind of problems works using the irrelevant vertex technique, and also our algorithm crucially uses irrelevant vertex. So irrelevant vertex. Yeah. So what Robertson and Seymour proved is more or less the following statement, that if G, so maybe I'll that's a theory. Yeah. If G has tree width larger or equal than some function of x and delta, yeah, so if the tree width of my graph is large enough constant, is large enough compared to the parameters of our problem, then there is a vertex u outside of the roots, outside of x, such that this x delta folio of G, so the thing that we want to compute is equal to the X delta folio of G minus. Yeah, so in other words, by deleting vertex U, I do not lose any of the rooted minors. Any rooted minor model can be somehow rearranged so that this vertex U is avoided, and therefore this vertex is irrelevant. So what was done, how Robertson and Seymour gave their cubic algorithm is that they gave a quadratic time algorithm to find an irrelevant vertex. Yeah, once the truth is large. Yeah, so they look at the proof of this theorem and they extracted a quadratic time algorithm to locate an irrelevant. Yeah, so then the algorithm is like locate irrelevant vertices as long as the tree width of the graph is larger than this function of our parameters, and otherwise run dynamically. Yeah, so as long as the tree width is large, I can find vertices that are provably irrelevant for the problem, and once the tree width drops to something small, then I can find a tree decomposition of the graph, and then I can employ the routine dynamic programming algorithmic techniques to just process the tree decomposition bottom up and understand the solution. Good. So they gave quadratic time algorithm to find irrelevant vertices. So then, because I'm extracting vertices one by one, this gives me a cubic time algorithm. Yeah, so just a basic application of irrelevant vertex technique gives me this additional order of an overhead. So what Kawabayashi, Kobayashi, and Reed did is just locate irrelevant vertex in time order of n, in linear time instead of quadratic. So then they got improvement to quadratic. But now you see, you looking at this scheme, that this is a little bit of a barrier, right? Because you now, in order to improve upon the quadratic time, you need to somehow get around the fact that you are locating irrelevant vertices one by one, yes? And sort of you expect that every location of an irrelevant vertex would require at least looking at the whole graph, so at least a linear time. Yeah, so you need to get around it. So people tried, and for many particular problems, like for instance, testing embeddability in a fixed surface, yes?
So does it mean that you can locate irrelevant vertex without reading this?
No. We can locate. Wait a minute. You will see where is the trick. How we are improving this.
No, but for this.
For this.
This is just big O of n, not m. So.
You mean that?
Why don't I have to read all edges?
They had it. They had in.
Maybe once, but not every time.
Yes, I think as far as I remember, they have a sparsification technique that at the beginning sort of is able to provide them an assumption that the number of edges, like they read the whole graph, they do some sparsification, and they work on a subgraph that has a linear number of edges. But it is more involved than just that. But they do this kind of a sparsification. Good. So what they do is locate vertex, irrelevant vertex in linear. Yeah, in linear in the number of vertices after the sparsification. So what people try to do, for example, for concrete problems like testing embeddability networks or testing embeddability in a fixed surface, and with good results, is to try to locate irrelevant vertices in larger batches. In the sense that if you have large tree width, then you do not expect really only one vertex to be irrelevant, because you know that if you delete this vertex, the truth will be still larger, it will be another irrelevant vertex. Yeah, so you expect a lot of vertices to be irrelevant. Yeah, so they were able to somehow structurally understand the graph and show that, for example, this half of the graph is irrelevant. Yeah? And then you can remove this half of the graph, and so on and so on. So you remove irrelevant vertices in a bounded number of, say, logarithmic number of rounds. And this is not what we do. We do something completely different. Namely, we still locate irrelevant vertices one by one, and we remove them one by one. But what we are doing, we are actually doing stuff on the algorithmic side, and we use data structures. So that every next irrelevant vertex will not be located in linear time, but in amortized subpolynomial time. So there will be some data structures trick, yeah, called dynamic tree width, so that every next irrelevant vertex will be located in roughly this one. So idea, use data structures to locate irrelevant vertices in amortized time n is small. Yeah. So then we find those irrelevant vertices one by one, and because there are n of them, we get running time n times m to small of 1. But this works only for step 1. In other, there are 3 more steps where we need to work with some recursion, so we do not get at the end n times m to small of 1, but we actually get m to 1 plus small. Good. Okay, so that's the basic idea, how this approach differs from the approaches from previous works. So now I can try to explain to you the consecutive steps that we are doing in our algorithm. And generally, these steps will be proving the theorem, giving an algorithm for larger and larger classes of graphs. And eventually, it will be an algorithm that will work on all graphs. So the first step, and this is the step on which I would like to sort of focus, because it's probably the most interesting and also the most accessible, is the step of working with apex minor figures. So step 1, apex minor. So the definition of an apex graph is the following. So I will say that a graph Q is an apex graph if Q can be made planar by removing one vertex. Yeah. So let's make an example, which will be an important example. So an example of an apex graph is what I will call an apex grid of order P. I will call it AP. I take a grid, a P times P grid, and I add one additional vertex that is adjacent to everybody. Does it make sense? So now observation is that those apex grids are actually kind of universal for apex graphs. Yeah, so observation, whenever Q is an apex graph, there exists a P such that Q is a minor of the apex grid of order P. Yeah. Why so? Because if I have an apex graph, I can look at the apex, look at the remaining graph, this graph Q minus U, where U is the apex. Yeah, this is a planar graph. So for large enough grid, it is a minor of this grid. Yes, every planar graph is a minor of a large enough grid. Just take plane and draw a fine grid and just draw those branch sets. Yeah. So now if this planar part is a minor of this grid, then I can find a Q as a minor of an apex grid by additionally mapping the apex U to the apex of the grid. So excluding an apex graph is the same conceptually as excluding some large enough apex grid. So we will now be working on the following variant of the folio problem, where conceptually speaking, we will be working on graphs that exclude AP for some fixed. But more precisely, the problem which we will be working with will be called folio or AP minor. And this is defined as follows. So what we are given is a graph G, root, delta, and a number P. Yeah. And the question is to either solve the problem, so either compute X delta folio of G. So this is what we are after. Or the algorithm may say I fail, and I fail because I get an AP minor model in G. Yeah, so the algorithm may say actually the graph is too complicated. It contains this minor model of AP. Yeah? And the goal is the time will be. Now I assume that the running time can depend also on this part. Okay, so this is the step where we will be using this kind of an idea of data structure of locating irrelevant vertices in subpolynomial amortized time using data structures in the most like vanilla way. All the further steps will be more complicated on the conception. So now I need to, in order to approach this problem, I probably need to tell you what is the dynamic tree width result. So the idea of dynamic tree width is to have a data structure, a robust data structure for graphs of bounded tree width that change dynamically over time. There will be a theorem, but let me just write this slowly. So imagine that G is a graph. Suppose G is a graph of tree width at most k, changing over time by edge insertions and deletions. Yeah, so I have a graph G. Yeah, it has a fixed vertex set. Yeah, and now I have a promise that at all times this graph will have tree width at most k. Yeah, but now it can change over time. Maybe the user will add this edge and then remove that edge and then add this edge and so on and so forth. So eventually over time, he can the user can just rebuild the whole structure of the graph. Yeah?
But the set of vertices is big.
The set of vertices. The set of vertices. So now our goal is to maintain along the user's updates a reasonable decomposition of the graph, because we always have a promise that the truth is at most k. Yeah? So then it is possible. there is a data structure that maintains a tree decomposition of G with at most 6k plus 5, as far as I remember. Yeah. In amortized time, okay, of 2 to the order of square root log n times log n. And don't care about this. What is important is that this is a polynomial. Yeah. So what does it mean amortized time? This is a standard measurement in dynamic data structure. It means that every single update can actually take a lot of time, but the average times, like whenever you look at the prefix of updates, yes, and you look at the average time used by an update, it will be like that. Yeah. So all in all, if I'm doing say n updates on the whole graph, I will use n times this time, so n to 1 plus small o. Yeah, even though a single update can take as much as the worst case. Yes. So this is a result that we had with Tukka Kojonen, Konrad Majewski, Wojtek Nadara, myself, and Marek Sokołowski at Fox last week. So this is the very first one. So I did not finish. I still have space here. Moreover, for every fixed sentence phi of logic CMSO2, one can also maintain whether the graph satisfies this. So, okay, if you don't know the logic MSO or its particular variant CMSO2, it's just some variant, some logical formalism for defining graph properties. For example, in this logic, you could state that the graph is free-colorable, or that the graph has a Hamiltonian path, using a sentence of fixed length. Yeah. So then, using this theorem, you could additionally maintain, for example, whether the graph is Hamiltonian or not. Yes, Martin?
So C is for counting.
Yeah, C is for modular counting predicates. So you can say there is a set that has even size. Good, but essentially what is, like, it is known that on the graphs of bounded tree, if any property that can be formulated in MSO can be computed, can be tested in linear time by making a linear time dynamic programming on the tree decomposition. And what this sentence says is that along with this decomposition that is here, we can also maintain the run of any reasonable dynamic programming algorithm. Yeah, in particular, any dynamic programming that that tests the satisfaction of some MSS. Good. So the idea is that we will be using this result, this data structure, to sort of process the graph on the fly, and on the fly find irrelevant vertices. Okay, so now we are sort of ready to approach solving this problem. Are we ready? Not quite. I still need to tell you how to certify that a vertex is irrelevant. How to expose a combinatorial structure in the graph that will certify that this vertex can be safe irrelevant. Yeah. So this is something called the flat wall theorem, and the irrelevant vertex rule for the flat wall theorem. And that's the basic tool developed in the graph minors series that is used for finding and removing the real value. So what is first of all, what is a wall? Wall is a specific graph. It looks like that. Oh, how do you draw a wall? That is yeah, this is a wall, a 3 × 5 wall. So I should have done it a little bit longer, but anyway. Yeah, so that's a wall. You typically draw it like that. In the literature, actually, it's actually the hexagonal grid as well. So you could draw it different. And each of those edges here can be actually a longer path. So this is a graph that I will call a wall. So wall is kind of a subgraph or subdivision variant of a grid. Nothing to say. For the flat wall theorem, which I will now state here somewhat somewhat informally, because the actual statement requires a few pages of preliminaries. This is the following. So imagine I've got my graph G, and G such that it excludes some clique minor for some fixed h. It excludes kh as a minor. And the tree width of my graph G is large. It's larger than some function of h and some parameter k that will be given. Essentially, k is the size of a flat wall that I want. Yeah. Then G contains a wall that is flat, and now I'll change the color after removal of I guess only depending on h, G of h. So what do I mean by that? I mean that in my whole graph, I can find a wall like that will be a k × k wall. Yeah. And it will be flat after putting aside a bounded number of vertices that I will call apices. Yeah. Again? Yeah, this was the next part of the sentence that I would like to continue with. Yeah. And this wall is flat in the following sense. Yeah. So look at the perimeter of this wall. And look at the connected component of the graph that contains the interior of the wall. Yeah, well, there is one, yeah, because all of those connections here are connected. Yeah, so here is some connected component containing the interior. It is called the compass of the wall. So then this connected component, yeah, this connected component admits, so flat means compass can be embedded in a disk with boundary. The perimeter of the wall, yeah, the perimeter is here, so it can be just drawn here. I will say here for the formality, possibly with flags. Possibly with flags means that actually what is happening here is not really a graph, but a graph that is being partitioned into things that look like that. So kind of triangles in the plane that are connected at the endpoints. Yeah, so the whole graph can be partitioned into those small sails, let's say, or flaps, as we call them. Yeah. And the graph can be drawn like that so that the crossings only happen inside the flaps. And the whole graph is drawn inside the flaps. So in other words, if you replace every flap by just a triangle, then the graph is plain. Yeah, so sort of you partition your graph into small pieces with boundaries of size 3. Yeah, so that the structure of those pieces you can draw planarly. The pieces are being embedded into those triangles, and inside the triangles, you have connection. Again?
Inside there is no restriction. Yeah.
Inside there is no restriction on that. Yeah. Yes.
But, how does it behave with respect to the wall?
The wall is a subgraph of that. And the wall is a subgraph of that, and it must be like rooted at the perimeter.
It goes through these plots.
Yes, it goes through these flaps. But observe that because flaps have boundary of size 3, you cannot really hide any larger part of the wall inside the flap. Because a wall is a bidimensional structure. Yeah, in a sense, like if I carve out a part of the wall containing 10 vertices, or I say 100 vertices, then it must have a perimeter of size roughly 10. Don't care at this level of technical of formality about the flaps. Imagine that this is just planarly embedded.
What does it mean that the wall is flat after removing some vertices?
So observe that those vertices here, like I said, I take the connected component. If I did not remove those vertices here, maybe this connected component would spill all around.
But that's not part of the wall.
That's not a part of the wall.
So you remove those vertices.
Yeah, I remove those vertices from the graph. After the removal, I look at the connected component, and this connected component can be drawn here. Yeah. So in particular, these inside of the wall cannot communicate with the outside of the wall, other than communication through the apices. Good. So that's the flat wall theorem. And the irrelevant vertex theorem says that if W is a large enough flat wall in G minus X, yeah, where X are the roots of our instance of folio that we are solving, then the central vertex is irrelevant. Yeah. So if I find such a structure here, and here I also have those vertices X, also apices, then I can claim that this vertex is irrelevant for the computation of the folio. This theorem, as stated here, is false. One requires one additional technical property from this theorem called homogeneity. And this homogeneity property essentially tells you that every small part of this wall is sort of behaving in the same way with respect to A pieces. So the A pieces have somehow the same connectivity to every part of this wall. But inside every flat wall, you can find a large flat subwall that is homogeneous. So whenever you find a large flat wall, you can actually extract stuff, extract a large homogeneous sub. So let's not think about homogeneity. Me neither, but yeah.
Say that the central vertex will be irrelevant within a flat wall, but here the wall is flat after removing those vertices, which means that with these vertices it is not irrelevant, or right?
Yeah, if I expose a large flat wall,
maybe let me say it different.
Yeah.
I can make any wall flat by removing some vertices.
Yes, but you remove here only a bounded number of vertices, bounded only in terms of the
irrelevant vertex theorem says nothing about what vertices I remove.
Yeah, it says nothing.
So
that is true.
Okay, so a vertex becomes irrelevant after removing these vertices.
No. A vertex, like, how to phrase this? Seeing this structure, yeah, for k large enough compared to the number of A pieces here, is sufficient to claim that the central vertex is irrelevant for the folio problem.
Okay, so you mean that W is large enough with respect to the number of removed...
Yes, the number of removed vertices is depending only on the excluded minor. Okay. It doesn't depend on k.
I was missing the statement of irrelevant vertices.
Yeah, if large enough flat wall, it's true, compared to the number of A pieces. As you can imagine, there is a lot of technical details here that I'm trying to hide under the carpet, but Bartek is sweeping those technical details from under the carpet, and I'm very glad for all those questions. Yeah, this means that we sort of understand it, hopefully. Good. But yes, this is a statement such that if you find this kind of a structure, you are sure that the central vertex is irrelevant. And you know by the flat wall theorem that if the truth is large, there will be a structure. But what is important for us?
We should find the fact that this is irrelevant is because that if there is a way to make this folio or to say in simpler stuff to route the disjoint paths. If there is a way with this vertex, then there should be a way without this vertex.
Yes.
Because
whenever you have some kind of a linkage here, disjoint paths flowing through this, because you have homogeneous, you have sort of uniform connectivity between here and here, and because you have a lot of possibility of routing things inside the wall, you can actually reroute things so that this vertex is avoided. That's the intuition. But it takes a paper to prove it. Good. So what is important is that if G is actually a P minor thing, yeah, so instead of assuming that I exclude a clique, I exclude some large apex grid, then no apex. These guys disappear. They cannot. And the intuition is that I cannot have an apex that is adjacent to the whole grid, because the whole wall. Because if it was adjacent to the whole wall, I would be able to find a model of AP. And once every apex is adjacent only to a small portion of the wall, I can actually carve out this portion of the wall and focus on some, I don't know, half by half wall here that is completely non-adjacent to this apex, and this apex disappears. Yeah, so I can get rid of A pieces when I'm working with AP minor figures. So this will be important for our current goal. Okay, so now we have actually all the ingredients to do the stuff on apex minor figures. So the algorithm is as follows. So first of all, point 0, assume G minus X is connected. Yeah, recall that we have, our graph looks like that we have a small set of roots, yeah, whose folio we want to prove, we want to compute, and here we have the rest of the graph. And I would like to assume that this rest of the graph is connected. And the point is that if this was disconnected, there were several connected components here, then I could compute the folio of disconnected of roots plus disconnected components, roots of this plus disconnected component, and so on and so on. And folio is a compositional problem. If I know folio of that, and I know folio of that, then it's not hard to show that you can compute the folio out of those of the combined graph. And here is actually why we are working with the folio problem. This wouldn't be the case if we were just focusing on, say, disjoint paths, or we were focusing on testing a particular H minor. Yeah, folio gives you a full information about the connectivity pattern within the graph, so that this information is composition. Good. So this is now the current assumption. We've got our roots, X, and the whole rest of graph G minus X connected. Okay, so let U1, U2, and so on, I don't know, probably N, let's call it N. This is an ordering, let me order the vertices, ordering of G, so that every suffix induces a connected suffix. Yeah, so I'm ordering the vertices. Here they are. These are the vertices of G minus X. Yeah, so that whenever I'm looking at the suffix, this suffix induces a connected suffix. And this is easy to do, because what I'm doing, I can just take any spanning tree of G minus X and just order it bottom up. And this ordering bottom up will have this. So now the idea that what we will be doing will be a, let's call it a technique. We will call it iterative decompression. Essentially, the idea is that we will first take all of those vertices, this whole G minus X, and we will contract it to a single vertex. Yeah, so that at the beginning, I start with graph, say G1, that looks like this X, plus one vertex that I will from now on depict in orange, call V star, and call the mega vertex. Yeah, because this is vertex that is composed of contracting all the vertices, and probably it is adjacent to all the people from X. No? And then we will be iteratively uncontracting vertices one by one from this mega vertex. Yeah, so in the first step, I will take vertex U1, yeah, and now move to the situation where the mega vertex is just the contraction of this suffix, and this U1 is doing like bloop and being uncontracted from V star. Then in the next step, I will uncontract the next vertex U2. So it will appear here, maybe like that, and it will be also adjacent like that. Yeah. So from this, I get G2, G3, and so on up to the last graph Gn, which is our original graph G. Yeah. So we are doing this kind of unconstructions. So this is precisely the moment when I do not want to erase this, because this is the moment when I will be using the dynamic tree of data structure to keep track of this graph.
The purpose, like the set of vertices changes.
Yes, the set of vertices is changing, yeah. I knew that I know that I said that that it should be fixed, but within this data structure, you can actually sort of model adding and removing vertices. Because what you can do, you can sort of, if you know that your whole graph at the end of the day will have at most n vertices, you can have like a set of n vertices at the beginning, and just have some of them marked as this is not really a vertex. It's just a virtual vertex that will be used eventually, that is not yet present in the graph. Yeah. So within this theorem, you can additionally have sort of markings, colors on vertices, and these colors can be used by the formula. And then the formula can just ignore the vertices that are not there. Well, they will be isolated, so they will be as singleton-backs. So yes, it's not a problem to within this theorem also encompass the possibility of adding an isolated vertex as an operation. So observation is that this chain of transformations from G1 up to Gn can be modeled by order of m operations of insert, delete, edge, and insert isolated vertex. I will not prove this claim, but I hope that you can believe me that you just count how many every original edge of the graph is being touched, and it is touched like 3 times. So then the idea is that we can sort of keep track of this chain of this sequence of graphs using our dynamic tree of data structure. At the beginning, the truth is trivial because the graph has actually like x plus 1 vertices, so this is bounded. Yeah.
Stop for a moment. I'm lost with this observation somewhat. So you say that it should be easy to see that we can model this with operations insert delete. And what is the reason again?
Essentially, whenever you are doing an uncontraction of a vertex from the mega vertex, yes, you need to introduce the edges that are incident to this vertex. So sort of every edge will be introduced in this at most once.
Uncontract these edges were at the mega vertex, right? But this mega vertex is still there, so you but now there was some guy which was isolated before, and now you want to put the edges in there.
Well, if it was isolated,
well, it wasn't in the graph; it was marked or something, right?
So you might introduce every edge twice. Yes, once for the first vertex. Second.
Yeah, because like once I introduce, once I uncontract the first endpoint, I make it adjacent to the mega vertex, so it's 1 edge. Yes. And once I uncontract the second one, I need to remove this edge to the mega vertex, and I need to add the so 3 times. Yeah, so constant number of times. That's it.
Why is the view is bounded?
That's a very good question. It is not bounded a priori. At the beginning, it is bounded, but at the end, the graph is Gn, which is the original graph, so we have a large tree. But the point is that once the tree becomes one larger than this function f there, yeah, once tree width of Gi is equal to this function f of hk plus 1, this function that guarantees us that there will be an irrelevant vertex, then we know there is an irrelevant vertex.
Modeled by a CMSL2 formula.
Yes. Yeah. So this will be more complicated. So bear with me. Actually, we know that there is a flat wall so far, and we still need to work a little bit with this problem. So I know that the truth is still bounded because it is this bounded function plus 1 only. So it is still within the limits. And I know that at this point, I can find in my graph a vertex that I can remove. Yeah. And get the graph simpler. And I can remove those vertices as long as the truth is that large. Yeah. So I will be just iteratively removing irrelevant vertices from the graph as long as the truth is that large until the truth again becomes small, and I can continue. The point being here that uncontraction of one vertex can increase the truth by only. So more precisely, once the truth is large, we know that there is a flat wall in this Gi minus x. Yeah, I remove x from the graph. Probably I put it like here. I'm actually thinking only about finding a flat wall in Gi minus x. Yeah. So I know that at this point the graph looks like that. Here I've got x. Here I've got my whole graph, Gi. And here I've got a flat wall. Yeah. So now there is a very good question: what happens in the mega vertex? Yeah, because I know that this is a flat wall in G minus x. I work under the assumption that I am apex minor free graph, so there are no apices. Yeah, the only apices are actually this x here. But this is Gi. Gi has this one pesky vertex, the mega vertex, that can be somewhere. For instance, it can be here, B star. Yeah, and it can be sort of still spoiling our wall. But that's actually still okay. If it's here, let me just toss away this half of the wall that contains this vertex. Yeah, I can always divide my wall into 3/4, just to make the wall square, and focus, zoom in with losing factor 2 on the size of the wall to the side of the wall that doesn't contain the mega vertex. So, all in all, we may assume that B star, the mega vertex, is outside of that.
It's also not in any of these flaps because flaps are also
Yeah, it is.
located.
Yeah. Flaps are part of the compass. Yeah. So now the irrelevant vertex theorem tells us that the middle vertex of this wall is irrelevant, but it is irrelevant in Gi, right? Because this is a flat wall in Gi. But observe that this is a flat wall in GI, but also in GI minus X, but also in G minus X. Because G minus X differs from this graph only by uncontracting the mega vertex to some connected blob here. Yeah, it doesn't affect at all what is happening inside the flat wall.
What if the inside of your flat wall is connected to X?
That's perfectly possible. That's okay. In the irrelevant vertex theorem, I could handle some apices. X will be those apices.
So actually, you
Yeah.
may have apices.
Yes.
So there are no apices, but there will be.
Yes, there will be apices. There will be apices, but the apices are controlled. They are the roots. What I really did not want is the mega vertex to be an apex. So it would be a catastrophe if this was an apex. Because if it would be an apex in GI, which would be okay for claiming irrelevant in GI,
Yes.
but then when I uncontract, suddenly there is like a billion of vertices that are connected all over the place in the flat. And then I cannot argue that the vertex is irrelevant also in G minus.
But as part of this, what is the problem if you have these extra G or H apices?
One of them can be.
Yeah, one of them can be the mega
Oh,
vertex.
what?
One of them could be the mega vertex. And then everything breaks.
Wow.
And this is why we need the next 50 pages of the paper.
Very inconvenient.
Yes. Okay, perfect. So what we actually do, we write a formula. Maybe I can already remove this board, or at least part of this board. Maybe this. We write a formula now with one free variable, phi of x, saying x is the central vertex of a homogeneous large enough flat wall that avoids the limit. So we write a sentence saying a vertex can be this guy. And this sentence being satisfied in GI implies that the irrelevant vertex is irrelevant in GI, but also it implies that it's irrelevant in the whole G. So then, assuming the tree is large, we know that this formula will have a solution. There will be a vertex satisfying that. We find it from the dynamic tree of data structure, and we remove it from there.
Here you just had a sentence.
That is true. This is the next statement that I wanted to say. Sentence I wanted to say. That you need to generalize this result from satisfaction of sentences to like having formulas with one free variables and being able to provide an example vertex that satisfies it. But this is like a routine. Once you understand how this result works, is you can just plug in, write some additional automaton, and there was already a ready interface in this paper so that this works very easy. Yeah, so you can generalize this result to finding example solutions. Yeah. So we write the sentence, and so then find solution phi as long as true is large and true. Yeah? And observe that actually we can end up removing quite a number of irrelevant vertices around. Yeah, just because the tree keeps being large, yes, but still every vertex will be eventually removed at most points. That's a new. Yeah. So along this whole sequence of graphs, this tree stays bounded, and we can use the dynamic tree data. So just wanted to say that writing this sentence is far from being trivial. You need to prove some combinatorial statements on the way. It's not terribly difficult, but there is still a lot of work. It probably takes 10 pages and 1 month of Jan's time to write it down. But it can be done. Good. What's the timing? Actually, not that great, probably. I just run out of time. This was step 1. Well, we did not write it really, right? We proved its existence. Okay, so this was step 1 of the algorithm, probably the most graspable and with a limited amount of time part of the paper, but also conceptually the most new, I think, because this is like application of this data structure tricks to finding irrelevant vertices. Step number 2 is working with already KT minor free graphs, but sort of compact ones where the whole graph is somehow well concentrated around X, for a good definition of being well concentrated. And it turns out that because of the structure theorem proved by Robertson and Seymour for H minor free graphs, these KT minor free graphs that are compact are actually very close to being already apex minor. They're apex minor free after removal of a bounded number of pieces. So you can sort of run this scheme a few times, every time either succeed in finding the folio, computing the folio, or identifying another apex. And you remove this apex, or you move it actually to X, and you repeat this only a bounded number. Yes.
Question. So this algorithm here was supposed to give the folio, or say
there is an.
Where was this instruction? Here is your apex.
I have a very good question. So if this formula has no solution, then this is a certificate that there must be an apex root SMI. Because you know that if there is none, then this formula will have a solution.
But you don't have a model.
Yes.
I didn't get it.
Also a good question. Out of this data structure, you can also get a model. So now you can write a formula saying, give me a model of AP. Yeah, and you can extract from the data structure the model of AP. Yeah, once you have this, you can have everything that is expressible in MSO, extract solutions. Another thing is that there is a quite simple binary search trick that allows you to find the models, assuming you have an oracle certifying that there is a model. I don't want to go into the details. It's another 10 minutes of algorithm. So the problem of finding actually the model can be reduced to deciding that there is a model. Good. So I was saying, so the next step is KT minor free graphs that are compact, and they are already being very close to apex minor free graphs. The next step is when you have KT minor free graphs that are not necessarily compact, so general apex minor. And the idea there is that you are doing some kind of a recursive scheme. If the graph is not compact around this set of roots X, then in fact there must be like a large portion of the graph that can be carved out from X using a small separator. And what you are doing, you are running recursively the algorithm on this part in order to understand its folio, to compute its folio, and you replace this part of the graph with a small graph with the same folio. This is a very common technique in parameter algorithm called protrusion replacement. Yeah, and now if you do this replacement, you did not change the folio of this because of the compositionality of the folio. So the problem is that maybe by doing this replacement, you actually like run a linear time algorithm to reduce just one vertex or a small portion of the graph. So you need to actually, so this technique is called recursive understanding, this replacement. So what we do in the paper, we need to give a linear time implementation of recursive understanding. And this linear time, almost linear time implementation essentially finds a lot of possibilities of this kind of replacements and do them in parallel. So that's another part of the paper, another 30 pages of technical stuff, and in particular finding efficiently those places where you can do the recursion. This requires all those Maxwell tricks. So there we use almost linear Maxwell. We use the technique of isolating cuts of Lee and Panigrahi, and we use those mimicking networks and some submodularity, Gomorrah-Hood trees, whatnot. So this is the part that I did not intend to speak about, so I will not. And finally, from KT minor free graphs, you go to general graph, and fortunately, this is actually pretty simple. You again reduce to compact graphs using this kind of tricks, and you use the fact that if you have a compact graph and you find a large click minor in this graph, so the whole graph is concentrated around the roots, and moreover, you have a huge click minor here, then actually the folio is already generic in the sense that you can realize every possible rooted minor. So you can just say everything. So yeah, this concludes the sketch of what is going on for the 4 steps. So maybe 2 sentences about the outlooks. We are pretty excited about this technique of using data structures to find irrelevant vertices. And at this point, also together with Dimitrios Tidikos, we believe that we can also compute in almost linear time the composition given by the structure theorem of Robertson-Seymour. So this is the composition into almost embeddable parts. But this will require at least a few months to write down because there's a lot of details and much more logic inside. A good open problem is whether all of this stuff can be lifted to testing topological minors, and we have no idea. Okay, I think, sorry for being slightly longer, but thank you for this.